All right, so 8.4, trigonometric substitution. This is not trigonometric integrals. When we start this section, you're not going to see sines and cosines and tangents inside of these problems. What you're actually going to see is you're going to see square roots. You're going to see radicals, okay? So you're going to see radicals like the following. Square root of a squared minus u squared, square root of a squared plus u squared, and square root of u squared minus a squared, which is in fact every variety that's possible right there, right? I can do the subtraction in either order of two values squared, or I can do addition of the two. These are the only three possibilities here. And the objective is going to be to eliminate this radical by using Pythagorean identities. Okay? Now, I'm going to show you every step of what I'm doing in two ways. I'm going to show it to you analytically. That means with the calculus, or in this case it'll be the trigonometry of how the process is going to sort of break down using algebra. And I'm also going to show it to you graphically in terms of a diagram. We all think a little bit differently, and so when I look at this, I think about the triangles. I think about the diagrams that I'm going to draw. But some of you are probably really going to like the algebra part that I'm going to write down, and you're going to think like that better. So just bear with me. You're probably going to like one or the other, and you can use either one you like, okay? But I want to show you both of them. All right, so there's three different options up there that I said, right? We've got the square root of a squared minus u squared, we've got the addition, and then we've got the subtraction in the other order. And they all have a different u substitution with trigonometry that works. So the correct u substitution for a squared minus u squared under the radical is to let u be a sine of theta. And this is all going to feel really weird until I actually do a problem, but I need to show you how all this develops before you can use it, okay? So here's the idea. If u is actually a sine theta, then that means I can take this equation, this is the analytical approach I'm doing right now, and I could replace the u with a sine of theta squared. If that's what u is, I could replace it. And of course, when we work these problems out, u is going to have a number. It's going to be 4 or something like that. Okay, it's not going to be a u, right? So the variable in the problem, I'm sorry, I said it backwards, but the variable in the problem is u. The a is going to have a value. I'm not going to have two letters involved. Okay, so taking a look at what we have here then, what you'll notice is that this is the square root of a minus a squared sine squared of theta. And they both have an a squared in them. Yeah? So I can think about basically factoring out an a squared, which leaves me with 1 minus sine squared of theta. Well, once I get things in factored form, one of the properties of radicals from way back when that you've seen before is that you are actually able to separate these square roots. Now, while I do this, let me also make note of the fact that what is 1 minus sine squared? That is cosine squared. So what is the square root of a squared? A. And what is the square root of cosine squared? That is cosine. Okay? And this works for negative pi halves to pi halves. Now, I don't think that in any of the problems you're going to run into any issues with the fact that things are going to be in the wrong, restricted domain or anything like that. But I'm mentioning that because it is a true piece of information. So this is analytically. So that's thinking about this analytically. Now I'm going to do it graphically. So what kind of triangles did we draw when we were in trig? Mostly. Nobody knows. They're virtually, except for two sections of trig, they're the only kind of triangles you ever drew. Right triangles, you got it. So we need a right triangle. Oh, Emily's going, really? I forgot about that. Yes, we did. We drew right triangles, didn't we? Now you remember. Okay, so here's a right triangle. Oops. And in my right triangle, I take this particular equation right here where it says u equals sine theta and think about solving it for sine theta. Sine theta would equal u over a. Right? Do you remember in terms of triangles, if I put an angle theta down here? How is sine determined with triangles? That is, the sides of the triangle. How are they related to the trigonometric function sine? Right, opposite over hypotenuse. So from my angle theta, the opposite side, which would be my vertical side here, is u. And then the hypotenuse, which is the side opposite the 90-degree angle, would be a. All good? Okay. The side that's missing at the bottom then, I can use the Pythagorean theorem to find that, correct? Okay, so this piece right here, let's just call it x for the moment. So I have x squared plus u squared equals a squared, and my goal is to figure out what x is. So I end up with x squared equals a squared minus u squared, and I square root. So x is equal to the square root of a squared minus u squared. Does that look familiar? That's what we're working with here, right? That's the third side. The third side is always the square root of what we're dealing with. That's why the a sine theta worked. That's why it was chosen. Okay? And this is really good because, of course, as you see that if u is equal to a sine theta, then I can take the derivative of this just fine, correct? What would it get? What's the derivative of a sine theta? A cosine theta. It's easy to work with. I would much rather take the derivative of a sine theta than I would want to take the derivative of the square root of a squared minus u squared. Because if I deal with that, I'm still going to have square roots involved. I'm also going to have an inside and an outside function. I've got kind of a mess going on, right? There's worse messes, but it's not near as pretty as taking the derivative of this trig function. Okay? So we're taking something that's messy and we're converting it into something that's much cleaner to work with. That's the idea. Okay, so this is my graphical thinking. Sort of a, I don't know, let me say a justification for why this works graphically. Okay, you ready for the next one? And take a look. We're going to do the same kind of thing, but we're going to do it for a squared plus u squared. So let me justify with you why a squared plus u squared will work to have a tangent theta, and we're going to do it analytically first. So this is the square root of a squared plus, and u is going to work out to being a tangent of theta. Okay, so a tangent of theta, and I square this, right? So I end up getting a squared plus a squared tangent squared theta. I can pull the a squared out, and I'm left with a 1 plus tangent squared. Now, I didn't show the in-between step on that one. I kind of just jumped over it, right, where I factored it out. But I factored it out and split the square roots at the same time. All right, so clearly a squared's square root is a. What is the square root of 1 plus tangent squared? Well, don't tell me it's 1 plus tangent. That is not true. But what is 1 plus tangent squared? Secant squared. In fact, I think I still have it on the board, don't I? So this is the square root of secant squared theta. So this actually ends up being a secant of theta. I'm realizing I forgot to show you one other thing on the other slide. We'll get back to there in a minute. I'll show it to you here and then we'll go back. Okay, so this is analytically. So if you're working with a problem that has a square root of a squared minus u or plus u squared, what you have is you have that u is equal to a of a tangent theta, and you can replace the square root with the expression a secant theta. That's what this information tells you. Okay, so can you just memorize it and not have to worry about the proving part of it at this point? Yes, because we actually showed why that's working for us. Okay, the pieces of information that you need to be able to employ and actually use in your problem are what u is equal to, and then of course we will find du, and what that square root ends up being equal to. Okay, let me do my triangle for this. Okay, so again, what kind of triangle am I drawing? It's a right triangle. Yes, it is. And on my right triangle, I need an angle of theta. And again, taking this equation and solving it for theta, this is tangent of theta equals u over a. Okay, so in terms of sides of triangles, what is tangent? opposite over adjacent. So if you're having trouble remembering sine, cosine, tangent, right, SOHCAHTOA was one of the acronyms that you probably saw in your trig class. And so tangent is opposite over adjacent. So opposite is U, adjacent is A. And the side that I'm missing, we'll call it C because we like to call the side C when it's the side of a triangle that's the hypotenuse. Then A squared plus U squared equals C squared. And I'm trying to solve for C. So what is C? It's the square root of A squared plus U squared, which should look familiar. That's where we started, right? So this expression of tangent of theta equals U over A is the right expression to make this work. Well, let me write this in. So what I wanted to show you at the end here too of each of these was that let me do the end of this one right now here. So this expression with the square root of A squared plus U squared, I wanted to relate it back to the fact that this ends up being equal to secant. So the square root of A squared plus U squared is actually related to side A. So that is this side right here and this side right here are related with what trig function? What trig function relates those two pieces of information? Secant or cosine, right? And I'm trying to show you why that this A secant theta works. So I'm going to relate them with secant for the moment. Well, you know what? Let me relate them with cosine so that I can show you that it still is okay. So I would think to use cosine if it were me. So cosine of theta is equal to adjacent, which is U, over the square root of A squared plus U squared. And I'm supposed to be trying to find an expression for this A squared here, right? That's my whole goal, is to get rid of that within this problem. So I'm going to multiply by the square root of A squared plus U squared. And that equals U over, and I'll divide by cosine. Okay? But division by cosine is the same as multiplication by the reciprocal of cosine. And what is the reciprocal of cosine? Secant. So the square root of A squared plus U squared is in fact secant. I think I left my letter. No, I read a letter wrong. I did. I wrote this down as a U. That was A. Sorry. There we go. Now fixed. Let me go back to do the first slide and do the same thing. So again, I'm trying to relate the side with the square root with the side with A. And that's actually still the same cosine I just did a minute ago, right? So the cosine of theta is equal to the square root of A squared minus U squared over A. And if I multiply this A to this side, I have this same A cosine theta. It's going to be equal to my square root. Okay, we have one more to justify before we can use them, okay? And it's the square root of the subtraction in the opposite order. Okay, so now instead of A squared minus U squared, I have U squared minus A squared. And the appropriate substitution to use is A secant theta. So if I'm going to use A secant theta, let's verify this square root's going to be equal to. So this is U squared minus, and then, I'm sorry, the U is A. Secant theta squared minus A squared. Okay, so this should start to feel like I'm doing the same thing again, right? So I have the square root of A squared secant squared of theta minus A squared. I can pull the A squared out, and I have a square root of secant squared of theta minus 1. What is the square root of A squared? It's A. I have one thing I forgot to mention on the last slide. No, I'm here. It's right here in this one. All right, and what is the square root of secant squared? Sorry, what is secant squared minus 1? Tangent squared. I'm sorry, I didn't hear it. I apologize. And then, of course, I'm going to square root this. Now, this is the only one where I have a catch. And the catch is that when I square root a tangent squared, it's not always positive. So I end up with two possibilities. One possibility is that I get a tangent theta. The other possibility is that I get negative a tangent of theta. Right, when we have something going on here with tangent and it has to do with the angles. So if 0 is less than theta is less than pi halves, we end up getting a tangent theta. But if we move on and we look in quadrant 2 from pi halves to pi, I actually get negative tangent values. Do you guys remember the acronym that we did, a smart trig class, and in the quadrant 2 tangent's negative? We didn't have that on the last one because it was secant, and we didn't have to deal with that way. I don't think I wrote it down. Yeah, I didn't write it down. Just a second. This quadrant was negative pi halves to pi halves. And in quadrants 1 and 4, secant and cosine are both positive. So I didn't have to deal with any pluses or minuses. But this tangent is defined from 0 to pi, and in quadrant 2, tangent is actually negative.
What was the second one?
The second one is negative pi halves to pi halves. It's quadrants 1 and 4. Okay, remember when we did trig, if you go up to pi halves, you go up to 90 degrees on the unit circle and then down the other one. And on the right-hand side of the graph, cosine is positive, so we don't end up having any square root issues, but we do with tangent. All right, I say we have issues. We just have to be more aware that when we take our derivative, we need to make sure that we're taking into account, especially if we're dealing with something that's got limits on it, right? Definite integrals that have the numbers on the top and bottom, we have to take a little bit more caution there. Any idea why I skipped this actually being able to be equal to pi halves, or for that matter, to being equal to 0 to pi? Why do they not? I mean, the other ones, I didn't make mention of it, these other ones all had, actually, I didn't even write it in. They're all less than or equal to. They don't have problems, if you will. I don't know that it matters if they're equal to, but the other ones don't have problems with the equal to. This one does. Do you know why? Do you remember from trig? Something special about tangent that didn't happen with the other ones? Oh, I guess actually I probably couldn't have put it on secant either. It's undefined. What happens there instead, Hannah? Remember? There's an asymptote. I have asymptotes on the graph of tangent, and I think I very quickly made a mistake over here. Same thing's going on secant. Secant also has asymptotes. Cosine doesn't, though. Cosine doesn't have any asymptotes. Secant does, so we don't get the ends of it either. Tangent has asymptotes, so we have issues. Again, it's not something that we really have to be too watchful for or anything, but it actually is part of why it's going on. All right, we are going to do one more set of triangles, or one more triangle, not set of triangles. I'm going to put a theta in here. And if I think about this, again, I've got secant of theta equals u over a. All right, so what is secant in terms of a triangle? Very good. It's a hypotenuse, so that's this one u. Over the adjacent, that's this one a. And we can do the Pythagorean theorem. I'm not going to waste a lot of time in doing so because it works the same way as the other ones. And obviously we're going to get u squared minus a squared because that was the point, right? Is that we got the same thing that this function's working out to being. And what's more is that if I relate to one another these two sides, how are those two sides? What trig function relates them? Tangent, right? Tangent of theta is opposite, which is the square root of u squared minus a squared, over adjacent, which is a. So I actually get a tangent of theta is equal to that square root of u squared minus a squared. And you might say to yourself, okay, where'd that plus or minus go? Because back over on the analytical side, I had a plus or minus. Well, I actually drew this triangle. In fact, I drew all of my triangles as though those triangles were inside of quadrant 1, didn't I? Mm-hmm. I wasn't being really very honest about it, right? Those triangles are in other places as well, and this one could be in quadrant 2. And if this triangle were drawn over here in quadrant 2, the x value, that is the horizontal value, would actually end up being negative down here, and so I would have gotten a negative a tangent theta. Okay? All right. We're going to do one problem before we go in this section. Okay, so you can see how it works and see that It isn't as bad as all of what I've made it out to be so far. So what you have to do is you have to take a look at the square root and identify which of the three cases you're in. Well, the first thing you should identify is it's one of the subtraction ones, right? So this is not case number 2. Is it 1 or is it 3? Remember how I defined them. It's 1 because A is my number and I've got the number at the beginning, right? So this is case number 1. So I'm going to sort of make myself a note that I'm in case number 1. The other thing I want to make note of is what A and X are, or in this case, yeah, my U is X. So my A is what? What is A in this problem?
4.
It's 4. And my U is what?
X.
It's X. Okay, so far so good? Okay, so what this problem number 1 then says I can do is that I can let U be A, I'm sorry, yeah, there it is, U be A sine theta. So U, or in this case X, because X is my variable, X is A sine of theta. Oops, and I've got an A, so I should fill that in too. How about 4 sine of theta? I also need to know what dx is. So what is the derivative of 4 sine theta? This is not a trick question, I promise. 4 cosine theta, right. And then the last piece of information that my case 1 gave me is it told me what the square root of 16 minus x squared would be if I made this U substitution. What did it say that the square root of 16 minus x squared would equal to? 4 something. For cosine of theta. And the fact that the dx and the derivative there are the same does not always happen. But so right here, when I was doing the notes, right, the top told you a squared minus u squared, and all of the analytical stuff we got to the bottom, or on all the graphical stuff when we got to the bottom, we found out that this square root was the same as a cosine theta. That final information and the initial information are the two pieces of information that we need to use inside of the problem. Okay, that allows me to rewrite this problem. It allows me to rewrite this problem in terms of theta, which I did not do a very good job of doing that right there, d theta. All right, so taking a look at this then, my antiderivative on top, instead of having square root of 16 minus x squared, what will I have? I'll have 4 what? Say it again, louder. Yeah. Right, 4 cosine theta. And the dx, well, the dx is also 4 cosine theta, isn't it? So the dx at the end is 4 cosine theta d theta. All right, the x on bottom gets replaced a little bit differently. Make sure I'm going to write this correctly. Okay, so here's where I tend to think in terms of triangles, okay? So I'm going to draw my triangle. I have to replace my x, and I don't want to replace it with inverse anythings or anything like that. That's not the goal. So in terms of this triangle, here's theta. I have, okay, this right here is my relationship that I've got set up. So sine of theta is x, is x over 4. So from theta, sine value is opposite over hypotenuse, so there's x over 4, and of course we've already established that this square root on the bottom is the 16 minus x squared. And the question is, in terms of this triangle then, how could I express what x is? Okay, or even better, if I were to do this triangle, how could I express what square root of 16 minus x squared over x is if I don't want to do it directly? So I'm going to pause right here and make a change so you can see how I would do it from my triangle perspective. And then we won't do the integration, but let me show you the setup for it. The relationship I'm supposed to be using is this one right here. Square root of 16 minus x squared over x. What relates those two sides of the triangles? Tangent or cotangent, depending on which one you're working with, right? So this is actually going to be cotangent, though, because the 16 minus x squared is the adjacent side instead of the opposite side. right? It's actually flipped upside down of what tangent would be. I'm seeing vacancy. Are we okay with that? All right, so tangent would be x over square root 16 minus x squared. We have square root 16x squared over x, so that's cotangent. Wow, that wasn't what I wanted. So I'm tempted not to replace things as they go unless it just happens to be nice and clean. I actually ended up having a dividing by x business in here. If I have that, I can set it up this way. The other thing I could do, let me say from where I was going earlier, is if you had done what we did and you replace this with 4 cosine theta, and you have the 4 cosine theta at the back, and you actually want to replace x, okay, instead of doing what I just did a minute ago. If you actually want to replace x, you've got to figure out the relationship between x and 4, because you want to actually have a relationship for just x. Well, how are x and 4 related? What trig function? Sine, right? Sine, in fact, it's right here. Sine of theta is x over 4. So I had it circled over here too. So I've had it in more than one place. You didn't notice that. I can replace that x then with 4 sine theta here. What's cosine theta over sine theta? Cotangent. So you get the same thing either way, okay? So I'm sorry. I know that I do this because I think pictures, and I know that not everybody does. So just bear with me as I think through my pictures, because that's where I get to my point. But you can think in terms of the variables in an analytical approach too, and you get the same thing either way. So we will solve this problem and pick up right here next time. We actually are really close to done, but I don't want to keep you after time. So.